You've been tracking the enigmatic body 3I divided by Atlas. You know it's the third interstellar visitor. You know it's massive, fast, and weird. But what you might not know is what's about to happen on October 29th. In just over 4 weeks, Atlas disappears behind the sun, hidden from every telescope on Earth. And according to Harvard astrophysicist Avi Loeb, that's not a coincidence. That's an opportunity. The opportunity to use the sun's gravity to swing itself into permanent orbit, to trap itself in our solar system forever. Now, here's where it gets wild. In the last 48 hours, new data dropped. The mass, at least 33 billion tons, way bigger than anyone thought. The chemistry breaking every rule we know. And that green glow everyone's been talking about, it happened at the exact moment it should have been impossible. We just analyzed Loeb's full interview, the one where he lays out every single anomaly, every statistical impossibility, every reason why this might not be what they're telling us it is, and we're going to break down exactly what he's claiming, what the data actually shows, and what happens when Atlas goes dark in 29 days. Because whether you think this is just a weird comet or something far more intentional, one thing is undeniable. October 29th is the moment everything could change. The maneuver window, the point of no return, and we're going to walk through exactly why Loeb thinks you should take your vacation before that date. Let's get into it. But first, if you enjoy deep dives like this, hit that like button and subscribe. And tell me in the comments where you're listening from, what time it is there, and the weirdest thing that ever happened to you. Chapter 1. October 29th changes everything. So let's start with what Avi Loeb actually said in this interview, because the way he opens his argument tells you everything about how he thinks. He doesn't start with speculation. He doesn't lead with the alien hypothesis. He starts with a number 20 kilometers. That's how big he initially calculated Atlas to be based on its brightness when it was first discovered, 20 kilometers in diameter. For context, that's bigger than Manhattan Island. That's twice the size of the asteroid that slammed into Earth 66 million years ago and ended the dinosaurs. That's massive for something that supposedly got ejected from another star system and has been drifting through the galaxy ever since. And here's where Loeb's mind immediately goes to the statistics. He says, "Look, we know roughly how much rocky material exists in interstellar space. We can estimate it based on what we see in star-forming regions, based on planet formation models, based on the amount of heavy elements floating around out there. And when you do the math, when you calculate how often a rock this big should randomly cross paths with our inner solar system, you get a number. Once every 10,000 years. Once every 10,000 years. And we've been systematically searching for interstellar objects for what? A decade? Maybe a little more if you count the years before we had the technology to really identify them. 1 decade of looking, and we find something that should only show up once every 10 millennia. Those odds are, to put it mildly, strange. But Loeb goes further. He points out that we'd already found 2 interstellar objects before Atlas, Oumuamua in 2017 and Boris in 2019. Both of them were small. Oumuamua was maybe 100 meters long, roughly the size of a football field. Borisov was similar, a few hundred meters across, normal-sized. So you can call anything from another star system normal. The distribution of objects in space follows a pattern. There are way more small rocks than big rocks. It's just basic physics. When planets form, when star systems throw material out into interstellar space, you get billions of pebbles for every boulder, billions of boulders for every mountain. So, statistically, we should be finding tons of little interstellar objects before we ever spot a big one. Loeb calculates that we should have discovered on the order of 100,000 interstellar objects the size of Oumuamua, before finding something as massive as Atlas, 100,000. And we'd only found 2. Now, you could argue that maybe our detection methods are biased toward bigger objects. Maybe the little ones are just harder to see, and Atlas only showed up first because it's bright and obvious. And that would be a fair point, except for one thing. Atlas wasn't supposed to be this bright at the distance where we found it. When Atlas was first spotted on July 1st, 2025, it was beyond Jupiter's orbit, way out there, where sunlight is weak and objects are usually dim. Most comets at that distance are practically invisible. They're frozen solid, inactive, just chunks of ice and rock drifting through the cold. They don't develop their characteristic coma, that glowing cloud of gas and dust, until they get much closer to the sun, usually inside Mars' orbit. But Atlas was glowing, not just a little. It was bright enough to be spotted easily, bright enough that initial calculations assumed it had to be huge to reflect that much sunlight. It was like watching a streetlight turn on in the middle of the Antarctic. It shouldn't be doing that yet. Loeb highlights this in the interview. He talks about how comets typically need to get within about 5 astronomical units of the sunday. That's 5 times the Earth's sun distance before solar radiation becomes intense enough to start melting the ice and creating the outgassing that makes them visible. Jupiter is more than 5 astronomical units out. Atlas was glowing when it was even farther than that, farther than it should, unless, and this is one of the first places where the alien technology hypothesis creeps in, unless it wasn't being heated by the sun at all, unless it was producing its own light. But let's not get ahead of ourselves. Let's follow Loeb's argument step by step, because this is where things start to stack up. This is where the coincidences begin to pile on top of each other, until you start to wonder if coincidence is the right word at all. The next thing Loeb points to is the trajectory, and this is where the fine-tuning argument really takes shape. When an interstellar object enters our solar system, it can come from any direction at any angle. There's no reason it should care about the plane our planets orbit in. That's our solar system's geometry, not theirs. An object from another star should arrive at a random inclination, a random orientation, totally unrelated to our ecliptic plane. But Atlas doesn't. Atlas arrives on a path that's aligned with the ecliptic plane to within 5 degrees. 5 degrees that's nearly flat. That's almost perfectly in sync with the orbits of Earth, Mars, Venus, Jupiter, all the inner planets. Loeb says the random probability of that happening is 1 in 500. 1 in 500. Not impossible, but rare. Rare enough to notice. Rare enough to make you raise an eyebrow. But it gets better, because Atlas doesn't just align with the plane. Its trajectory brings it close to multiple planets. Really close. On October 3rd, just a few days from now, as of this recording, Atlas will pass within 29 million kilometers of Mars. That's close, in astronomical terms. Close enough that NASA's Mars Reconnaissance Orbiter is going to try to image it with the HiRiser camera. And it doesn't stop there. Atlas also makes relatively close approaches to Venus and Jupiter. All 3 planets. All at points in their orbits where the timing just happens to line up with Atlas passing through. Loeb ran the numbers on this too. He calculated the combined probability that an interstellar object on a random trajectory would pass as close as Atlas does to Jupiter, Mars, and Venus at the times when they're in the right positions in their orbits. The answer? 1 in 20,000. 1 in 20,000. Think about that for a moment. We're not talking about one coincidence anymore. We're talking about multiple coincidences stacked on top of each other, and the size, the brightness, at a distance where it shouldn't be bright. The alignment with the ecliptic plane, the close passes to 3 different planets. Each one individually might be explainable as just random chance, but together, Loeb makes a comparison in the interview. He says, you can argue that each individual thing is just a coincidence. The trajectory is random. It just happens to be aligned. The close passes are luck. The timing just worked out. But at some point, when you keep rolling sixes over and over again, you have to start wondering if the dice are loaded. And then he drops the big one. The thing that, if true, would be the most damning piece of evidence for intentionality. Atlas arrives at its closest point to the Sun, its perihelion, on October 29th. And on that date, Earth will be on the exact opposite side of the Sunday. We won't be able to see it. Every telescope on Earth will have the Sun directly between us and Atlas. It'll be in solar conjunction, completely hidden from view. Loeb says, this could be intentional. This could be the perfect time to make a maneuver. If you wanted to use the Sun's gravity to slow down, to change your trajectory, to insert yourself into an orbit around the Sun without being observed, this would be the moment to do it behind the Sun, out of sight. He calls it a reverse solar oath maneuver. Normally, spacecraft use the oath effect to speed up. You fire your engines when you're moving fastest, when you're closest to a massive object like the Sun, because that's when a little bit of thrust gives you the biggest change in velocity. But you can also use it in reverse. You can fire your engines to slow down, to bleed off speed, to let gravity capture you into an orbit. And if Atlas were to do that, if it were to make that maneuver on October 29th, while we can't see it, it could effectively trap itself in our solar system permanently. It wouldn't just pass through and leave like a normal interstellar object. It would stay orbiting the Sun, looping back around, hanging out in our neighborhood indefinitely. Loeb points out that the arrival date at perihelion, the fact that it's hidden from Earth at that exact moment, adds another layer of improbability. If you were to take Atlas's trajectory and just randomly vary its speed slightly, shift its arrival time by a few weeks earlier or later, the odds that it would arrive at perihelion precisely when Earth is on the opposite side of the Sun are slim. Not impossible, but slim. Just another thing that lines up a little too perfectly. And this is where Loeb pivots to the implications. He says, look, if this is alien technology, then it's choosing the optimal moment to make a move. The optimal point for a braking maneuver is at perihelion when you're closest to the Sun and gravity is strongest. And it's obscured from our view by the Sun itself. That's not just tactically smart. Is the kind of thing you'd do if you didn't want to be observed making course corrections. Now, he's careful to frame it as a possibility, not a certainty. He uses phrases like, could be, and if it were, technological, and this would allow. He's laying out a scenario, exploring a hypothesis, but the implication is clear. The setup is too good. The timing is too convenient. The trajectory is too fine-tuned. And that's just the beginning of his argument. That's just the orbital mechanics. He hasn't even gotten to the visual observations yet, the chemical anomalies, the things that were spotted by Hubble and Webb and all the other telescopes that have been tracking this object for the past 3 months. But already, just from the trajectory alone, you can see why Loeb thinks this deserves serious attention, why he thinks we should at least consider the possibility that we're not looking at a random cosmic iceberg, but something with intent behind it. Chapter 2. Bigger than Manhattan. So, let's dig deeper into this size problem, because it's not just about Atlas being big. It's about what that size means for our understanding of how interstellar objects should behave, how common they should be, and what we should have found before we ever spotted something this massive. When Loeb talks about the 20 kilometers estimate in his interview, he's pulling from those initial brightness calculations. The way astronomers figure out the size of a distant object is pretty straightforward in principle. You measure how much sunlight it reflects. You estimate how reflexive its surface probably is. That's called the albedo, and you work backward to calculate how big it must be to produce that much reflected light. For Atlas, those early calculations kept spitting out the same answer, 20 kilometers, and Loeb immediately recognized that as a problem. Not because 20 kilometers is impossible for a comet. We've seen comets that big in our own solar system, because finding one that size as an interstellar visitor, this early in our search, breaks the expected distribution. Here's the thing about space debris. Whether we're talking about asteroids, comets, interstellar rocks, whatever, they follow what's called a power law distribution. That means for every big object, there are exponentially more smaller objects. If there's one rock that's 10 kilometers across, there might be 100 rocks that are 1 kilometer across, and 10,000 rocks that are 100 meters across, and 1,000,000 rocks that are 10 meters across. The numbers explode as you go smaller. This pattern shows up everywhere in nature. It's how crater sizes work on the moon. It's how earthquake magnitudes distribute. It's how city populations arrange themselves. Big things are rare. Small things are common. The universe doesn't make as many mountains as it makes pebbles. So when Loeb ran the numbers on interstellar objects, he expected that pattern to hold. And if it does, if the distribution follows the same power law we see everywhere else, we should have catalogued thousands, maybe tens of thousands of Oumuamua-sized objects, those 100 mi scale rocks, before we ever got lucky enough to see something as massive as a 20 kilometers comet. But we hadn't. We'd found exactly two, Oumuamua and Borisov, both small, both in the 100 to few hundred mi range. And then boom, Atlas shows up. And it's potentially 100 times bigger in diameter, which means thousands of times more massive in volume. Loeb says this in the interview. He says, "Given the limited reservoir of heavy elements in interstellar space, we should have discovered on the order of 100,000 interstellar objects on the scale of Oumuamua before finding Atlas. 100,000. And we'd only detected 2 interstellar objects previously. Now, here's where the argument branches. You can interpret this discrepancy in a few different ways. Maybe our detection methods are just really bad at spotting the small stuff, and we're only catching the big bright objects. That's possible. Telescopes have limits. Small, dark rocks are hard to see. Or maybe the initial size estimate was wrong. Maybe Atlas isn't actually 20 kilometers across. Maybe the brightness we were seeing came from something other than a giant solid nucleus reflecting sunlight. Maybe it was surrounded by a huge cloud of gas and dust that made it look bigger and brighter than it really was. And as it turns out, that second possibility is closer to what we now think is true. More recent observations, particularly from the Hubble Space Telescope, have refined the size estimate considerably. As of late August, Hubble data suggested that the upper limit on Atlas's diameter is about 5.6 kilometers. Still big, definitely bigger than the previous interstellar visitors. But not 20 kilometers, not Manhattan-sized. 5.66 kilometers is more reasonable. It's still unusual, still larger than we'd expect to find this early, but it's within the realm of possibility for a natural comet. It doesn't completely break the statistical model the way a 20 kilometers object would. But here's where things get interesting again. Because just this week, just in the last 48 hours, new data came out that complicates the picture all over again. Loeb and his colleagues published a new analysis, not yet peer-reviewed, looking at Atlas's trajectory with incredible precision. They compiled data from 227 observatories around the world. Over 4,000 individual observations spanning several months. and they measured exactly how Atlas was moving through space. And what they found is that Atlas shows almost no non-gravitational acceleration. Let me explain why that matters. When a comet gets close to the Sun and starts to heat up, the ice on its surface sublimates. It turns directly from solid to gas, and that gas jets off into space. When gas jets off one side of a comet, it acts like a tiny rocket engine. It pushes the comet slightly, changing its trajectory in ways that gravity alone wouldn't predict. Astronomers call this non-gravitational acceleration, and it's one of the defining characteristics of active comets. You can measure non-gravitational acceleration by tracking a comet's position over time and comparing it to where it should be if gravity were the only force acting on it. If the comet is off by a little bit, if it's ahead of or behind where pure gravity would put it, that tells you the outgassing is pushing it around. Atlas, according to this new analysis, shows almost none of that. Its position matches a purely gravitational trajectory to within incredibly tight margins. The upper limit on its non-gravitational acceleration is less than 15 meters per day squared. That's tiny. That's way smaller than what you'd expect from a comet that's actively outgassing. And we know Atlas is outgassing. The Webb Space Telescope observed it on August 6th and measured the gas coming off its surface. The mass loss rate is about 150 kilograms per second. That's a lot of material. That's enough gas to produce measurable thrust, enough to nudge the comet's trajectory detectably. So, why isn't it nudging? Why is Atlas moving like it's only feeling gravity when it's clearly spewing gas into space? Lowe's answer is simple. It's too massive. If Atlas is heavy enough, if it weighs enough, then the thrust from outgassing won't move it much. It's like trying to push a cruise ship with a leaf blower. The force is there, but the mass is so large that the acceleration is negligible. So, they did the math. Given the observed outgassing rate and the absence of detectable non-gravitational acceleration, what's the minimum mass Atlas could have? The answer they got is 33 billion tons. 33 billion tons. That's the lower bound. Atlas has to weigh at least that much, or else we'd see it getting pushed around by its own gas jets. And if it weighs 33 billion tons, and you assume it's made of rock and ice with a density similar to other comets, you can calculate a minimum diameter. It comes out to more than 5 kilometers, possibly significantly more, depending on how dense it actually is. So we're back to a big object. Not 20 kilometers. Probably not, but definitely on the large end. Definitely more massive than any other interstellar object we've seen. Loeb points out that this makes Atlas 3 to 5 orders of magnitude more massive than Oumuamua or Borisov. That's a factor of 1,000 to 100,000 times heavier. And that brings us back to the original statistical problem. If Atlas really is this massive, then finding it this early in our survey of interstellar objects is, in Lowe's words, a major anomaly. It's like flipping a coin and getting heads 1,000 times in a row. Could it happen? Technically, yes. Is it likely? No. But there's another way to interpret the 33 billion ton number. Another possibility that Lowe hints at but doesn't fully commit to in the interview. What if Atlas isn't a solid rock? What if it's hollow? What if it's a shell, a structure, something with a lot of volume, but not much mass per unit volume? If you wanted to build a spacecraft capable of traveling between stars, you wouldn't build it out of solid metal. That would be insanely heavy, insanely expensive in terms of energy to accelerate and decelerate. You'd build a shell, a thin outer structure with lots of empty space inside. That's how we build ships on Earth. That's how nature builds things too. Bones are hollow. Plant stems are hollow. It's an efficient way to get strength without weight. A hollow structure with a diameter of 10 or 15 or even 20 kilometers could easily weigh 33 billion tons if the shell were thick enough. And it would look from the outside like a giant solid object. It would reflect sunlight like a big rock, but it wouldn't behave like a big rock when you measured its mass. Loeb doesn't say this explicitly in the interview. He dances around it. He talks about how we shouldn't judge a book by its cover, how the chemical composition of Atlas's surface, the CO2 and water ice we're detecting, could just be material that collected on its exterior as it traveled through interstellar space. Frost on the windshield, basically. But the implication is there. If you're open to the idea that Atlas might be technological, then the 33 billion ton mass suddenly becomes less of an anomaly and more of a data point. It's heavy, but not as heavy as a solid rock that size would be. It's massive enough to resist the thrust from outgassing, but light enough that you could imagine it being constructed rather than formed naturally. And this is where Loeb's argument starts to feel less like a single piece of evidence and more like a web of interconnected oddities. The size is weird. The trajectory is weird. The timing is weird. The lack of non-gravitational acceleration given the observed outgassing is weird. None of these things individually proves anything, but together they paint a picture of an object that doesn't quite fit the mold. Loeb acknowledges this tension. He says, by far the most likely outcome will be that Atlas is a completely natural interstellar object, probably a comet. He's not claiming certainty. He's not saying it's definitely alien technology, but he is saying that the data we have right now doesn't conclusively rule it out. And in his view, that's enough to justify taking a closer look. Enough to warrant using every telescope, every spacecraft, every observational tool we have to study this thing while it's still here. Because here's the thing about interstellar objects. They don't stick around. They pass through, and then they're gone back out into the void, unreachable for the rest of human history. If Atlas is just a comet, we'll learn a lot about comets from other star systems, and that's valuable. But if it's something else, if there's even a 1% chance it's something else, then missing the opportunity to study it carefully would be one of the biggest mistakes humanity could make. So that's the size argument. That's the mass problem. Atlas is big, probably bigger than it should be for an interstellar visitor we'd find this early. It's heavy, 33 billion tons at minimum, but maybe not as heavy as a solid rock that size would be. And those facts, combined with everything else about its trajectory and timing, make it just strange enough to warrant the question Loeb keeps asking. What if? Chapter 3. The trajectory is fine-tuned. Let's talk about the path this thing is taking through our solar system, because this is where the fine-tuning argument really starts to build momentum. When Loeb walks through the trajectory analysis in his interview, he's not just pointing at one coincidence, he's stacking them. Layer after layer of orbital mechanics that, when you look at them individually, seem unlikely but possible, and when you look at them together, start to feel deliberate. First, the ecliptic plane alignment. Our solar system is relatively flat. The 8 planets orbit the Sun in roughly the same plane, like a dinner plate with the Sun at the center. This plane is called the ecliptic, and it's a fundamental organizing principle of our local cosmic neighborhood. Everything that formed here, everything that coalesced out of the original protoplanetary disk billions of years ago, remembers that geometry. Asteroids mostly orbit near the ecliptic. Comets from the Kuiper belt are tilted, but still loosely related to it. But interstellar objects shouldn't care. They come from other star systems with their own planes, their own orientations, their own rotational axis. When something arrives from outside, it should come from a random direction at a random angle. The odds that it would happen to align closely with our ecliptic plane are slim. Not impossible, just slim. Loeb calculates it at about 1 inch 500. That's a 0.2% chance. If you surveyed 500 random interstellar objects, you'd expect one of them to align this closely by pure chance. An atlas is only the third one we've ever seen. So already we're looking at something that's beating odds of roughly 500 to 3. Unlikely, but not absurd. But then you add the close approaches. Atlas doesn't just pass through the solar system at some arbitrary distance from the planets. It passes close to 3 of them: Mars, Venus, and Jupiter. And not just close in space, but close in time. It arrives at each planet's orbit when that planet happens to be nearby. Think about what that requires. The planets are all moving. Mars takes about 687 days to orbit the Sunday. Venus takes 225 days. Jupiter takes 12 years. They're all at different distances, moving at different speeds, and they're only in specific locations at specific times. For an interstellar object to pass near all 3 of them during its flyby, the timing has to line up perfectly. Loeb did the math on this too. He looked at Atlas's trajectory and calculated the minimum distances it achieves relative to each planet's orbit, not just in space, but accounting for where the planets actually are when Atlas passes through. The combined probability of all 3 close approaches happening by chance, given a random arrival time and trajectory, comes out to about 1 inch 20,000. 1 inch 20,000. Now, we're not talking about 500 to 1 odds anymore. We're talking about tens of thousands to 1. And that's just for the planetary encounters. That's not counting the ecliptic alignment, which is a separate statistical role. On October 3rd, just days from now, Atlas will pass within about 29 million km of Mars. In cosmic terms, that's basically a near miss. It's close enough that NASA is planning to use the high-rise camera on the Mars Reconnaissance Orbiter to image Atlas directly. HI is designed to photograph the Martian surface at extremely high resolution, good enough to see individual boulders and rover tracks. Turning it toward Atlas should give us the best look yet at what this object actually looks like, potentially separating the nucleus from the surrounding coma and dust cloud. But here's the really interesting part. The minimum orbit intersection distance, the closest Atlas's trajectory gets to Mars's entire orbital path, is only 2.7 million km. 2.7 million. That's a tiny gap in astronomical terms. If Atlas's orbit were shifted just slightly, if it had arrived a little earlier or a little later, or if its path were tilted by just a few degrees, it could have come even closer. It could have intersected Mars's orbit at a point where Mars itself was present. Loeb points this out in the interview. He says, "This fine-tuning, this close approach to Mars, combined with the approaches to Venus and Jupiter, suggests a trajectory that's either extraordinarily lucky or carefully planned. And if it's planned, if there's any intentionality behind it, then the October 3rd Mars encounter might not be just a flyby. It might be an opportunity. An opportunity to do what? Well, that's where things get speculative. Loeb suggests that if Atlas were a technological object, a spacecraft or probe of some kind, then passing close to Mars would be an ideal moment to deploy something, a smaller probe, a lander, a scout. You could release a secondary object that makes a minor course correction and intercepts Mars while the main body continues on toward the Sunday. He even calculates the parameters. If Atlas released a precursor probe that traveled ahead of it and sideways by about 30 million kilometers, that probe could reach Mars around October 3rd, right when Atlas makes its closest approach. The ejection speed needed wouldn't be huge, a few kilometers divided by s, easily achievable, with even modest propulsion. And from Earth we wouldn't see it. We can't track objects that small at that distance. Our telescopes can resolve things down to maybe 10 or 20 meters at Jupiter's distance, but not much smaller, and certainly not if they're deliberately trying to stay hidden. Is there any evidence that Atlas has deployed anything? No, none. This is pure speculation. But Loeb's point is that we should be looking. We should be watching Mars carefully during and after the October 3rd encounter. If anything unusual shows up in Martian orbit, if any of the spacecraft around Mars detect anomalies, that would be significant. And then, there's the Venus pass. Atlas will also make a relatively close approach to Venus, though not as close as Mars, and Jupiter, farther out in its orbit, will also have an encounter, though at a greater distance. The fact that all three happen during a single pass through the inner solar system is again statistically unusual. Not impossible, but unusual. But the timing of the perihelion, the moment Atlas reaches its closest point to the Sun, that's where Loeb really focuses his attention, because perihelion happens on October 29th, and on that date, Earth will be on the exact opposite side of the Sunday Atlas, will be in solar conjunction. We won't be able to see it. Every ground-based telescope will have the Sun directly in the way. Even space-based telescopes that aren't affected by daylight will struggle to observe it because the Sun's glare drowns out everything nearby. Loeb calls this a hidden vantage point. He says if you were designing a trajectory that allowed you to make a maneuver unobserved, this would be it. Perihelion is the optimal location for a braking maneuver because that's where the Sun's gravity is strongest, and the Orth effect, the way orbital mechanics amplifies thrust when you're moving fast near a massive object, works in reverse. You can fire engines to slow down to bleed off velocity, and the Sun's gravity helps capture you into an orbit. If Atlas wanted to stay, if it wanted to transition from a hyperbolic escape trajectory to an elliptical bound orbit, October 29th would be the time to do it, and we wouldn't see it happen. We'd only know afterward, when Atlas re-emerges from behind the Sun in late November or early December, and we calculate its new trajectory and realize it's no longer leaving. Now, does Atlas have engines? Can it make course corrections? We have no idea. There's no evidence of propulsion. There's no heat signature, no exhaust plume, nothing that screams rocket motor. But if you're an advanced civilization building interstellar probes, you're probably not using chemical rockets that belch fire and smoke. You're using something more efficient. Ion drives maybe, or magnetic sails, or propulsion systems we haven't even conceived of yet. The point is, a technological object doesn't have to look like a science fiction spaceship. It doesn't have to have glowing engines and running lights. It could look like a rock. It could be covered in ice and dust, insulated, camouflaged, and it could make subtle adjustments to its trajectory that we'd only notice if we were watching extremely carefully. Loeb acknowledges this in the interview. He says we need to monitor Atlas closely during the perihelion pass. We need to use every available spacecraft, every probe in the inner solar system to track it as precisely as possible. ESA's JUICE spacecraft, which is currently en route to Jupiter, will have a good view of Atlas in November. NASA's Juno probe, already orbiting Jupiter, might be able to observe it later. Mars orbiters will watch it in early October. We should be throwing everything we have at this object to make sure we don't miss anything. Because if Atlas does make a maneuver on October 29th, if it slows down and captures itself into orbit, the implications are enormous. It would mean we have a visitor that's not just passing through. It would mean something is staying. Something is setting up shop in our solar system, and we'd have about 6 weeks from late November when it re-emerges until late December when it makes its closest approach to Earth to figure out what it is and what it wants. Loeb is careful to frame this as a low probability scenario. He says the most likely outcome is still that Atlas is a natural comet that will pass through and leave like every other interstellar object. But he also says the possibility, however small, deserves serious attention because the cost of being wrong, of missing a genuine technological visitor because we dismissed it too quickly, is far higher than the cost of investigating thoroughly and finding out it's just a comet. And that's really the heart of his argument. It's not that Atlas is definitely alien technology. It's that the data we have so far doesn't rule it out. And the trajectory is unusual enough that we should be watching very, very carefully. The ecliptic alignment, the planetary encounters, the timing of perihelion, all of it stacks up into a picture of an object that's either phenomenally lucky or following a plan. Loeb uses a gambling analogy at one point in the interview. He says, if you walk into a casino and see someone roll double sixes 10 times in a row, you don't immediately conclude the dice are loaded. It could happen. The odds are about 1 in 60 million, but it's possible. But if you see it happen, you'd probably want to take a closer look at the dice. You'd want to check if something funny is going on. That's all he's asking. Let's take a closer look. Let's check the dice. The trajectory of Atlas, the fine-tuned path it's following through our solar system, is one of those moments where the dice keep coming up sixes. And Loeb is saying loudly and repeatedly that we should at least consider the possibility that the game isn't entirely random. Chapter 4. No tail, just headlights. Now, we need to talk about what Atlas actually looks like, because this is where the visual observations start to clash with what we expect from a typical comet. And it's also where Loeb makes one of his most striking claims in the interview, the one about headlights. Comets are easy to identify, Loeb says. Just like zebras are identified by their stripes, comets are identified by their tails. It's their signature feature. As they approach the sun and heat up, ice on their surface turns directly from solid to gas, a process called sublimation. This creates a glowing cloud of gas and dust around the nucleus, called a coma, and a tail that streams behind the comet, pushed by solar wind and radiation pressure. The tail always points away from the Sunday always. It doesn't matter which direction the comet is moving. The tail is determined by the sun's radiation and the solar wind, so it streams outward from the sun like hair blowing in a breeze. You can use this to identify a comet instantly. Find the fuzzy object. Look at which direction the tail points, and you know where the sun is relative to it. But when the Hubble Space Telescope imaged Atlas on July 21st, something looked wrong. Hubble captured a teardrop-shaped cocoon of dust coming off the nucleus, and there was a hint of a tail, but the orientation wasn't quite right. Instead of a clear tail streaming away from the sun, there was an extension of scattered light pointing toward the sun, forward, facing, like the comet had headlights instead of a tail. Now, before we go too far down this path, we need to be careful about how we interpret telescopic images. Astronomy is hard. When you're photographing an object that's moving at interstellar speeds millions of miles away, exposure times matter. The object moves during the exposure, and that motion can create smearing effects. You get a light trail in the direction the object is traveling. And if that direction happens to be toward the sun, it can look like a forward-facing glow, even though it's really just motion blur. NASA scientists were quick to point this out. They said the apparent extension toward the sun in the Hubble image was likely an artifact of the imaging process. The comet was accelerating toward the sun, and Hubble tracked it during the exposure, which caused background stars to streak and potentially created a false appearance of a forward tail. But Loeb wasn't entirely convinced. He co-authored a paper with colleagues asking whether Atlas could be alien technology, and one of the pieces of evidence they cited was this unusual forward glow. They argued that while smearing effects could explain part of what we're seeing, the brightness and structure of the extension didn't quite match what you'd expect from pure motion blur. And then in late August, something interesting happened. the Gemini South Telescope in Chile captured new images of Atlas, and this time there was a clear tail. A faint tail streaming away from the sun, exactly where you'd expect it. By late August, Atlas had developed cometary behavior that looked completely normal. The scientists who analyzed those images said it confirmed what they'd suspected all along. Atlas is a comet. It's outgassing. It's producing a coma and a tail. Case closed. But Loeb points out that the timing is interesting. For the first month and a half after discovery, Atlas showed ambiguous visual features: the forward glow, the lack of a clear tail, the unusual brightness for an object so far from the Sunday. And then, right around the time it crossed inside Mars's orbit and solar heating really ramped up, it started to look more like a normal comet. He uses a book analogy in the interview. He says we shouldn't judge a book by its cover. The fact that Atlas now has a cometary tail doesn't necessarily tell us what's underneath. The surface could be covered in ice and dust that collected during its journey through interstellar space. Frost on the windshield, basically. And as that frost sublimates under solar heating, it produces exactly the kind of tail you'd expect from a comet, even if the object underneath isn't a natural chunk of ice and rock. This is speculative. Obviously, there's no direct evidence that Atlas has a different composition beneath its surface. But the argument is that visual appearance alone isn't conclusive. A technological object traveling through space for millions of years would accumulate debris, interstellar gas, ice particles, cosmic dust. All of it would stick to the surface and freeze. By the time it arrived in another star system, it would look like a comet from the outside, even if it wasn't one on the inside. And then there's the green glow. This is one of the most recent developments, and it's genuinely puzzling even to scientists who are absolutely convinced Atlas is natural. On September 7th, during the total lunar eclipse, 2 astrophotographers in Namibia captured images of Atlas under unusually dark skies. The eclipse dimmed the moon completely, eliminating a major source of light pollution, and they were able to get deep exposures of the comet. What they saw was striking. Atlas was glowing green, vivid, unmistakable green. Green comets aren't unheard of. We've seen them before. The color usually comes from diatomic carbon, a Me molecule made of 2 carbon atoms bonded together. When diatomic carbon is hit by ultraviolet light from the sun, it fluses, emitting visible light in the green part of the spectrum. It's the same principle as a fluorescent light bulb. Energy goes in at one wavelength, light comes out at another. So, a green glow on a comet is normally a sign that diatomic carbon is present in the coma, is being produced by the sublimation of organic compounds on the comet's surface. Nothing unusual, nothing anomalous, except that spectroscopic observations of Atlas taken just a month earlier in early August showed very little diatomic carbon. In fact, astronomers at Kitt Peak Observatory in Arizona found that Atlas was among the most carbon chain-depleted comets known. It had unusually low levels of the molecules that normally produce green fluorescence. So, how did it turn green in September? Where did the diatomic carbon come from? One explanation is that it was always there, just buried beneath the surface. As Atlas got closer to the sun and heating intensified, deeper layers of ice melted away, exposing fresh material that contained more carbon compounds. The green glow could be a sign that we're now seeing interior ice that was previously locked away. Another explanation proposed by Loeb in a blog post after the green images came out is that the color might not be from diatomic carbon at all. It might be from cyanide. The Very Large Telescope in Chile detected a steep rise in cyanide production from Atlas in late August, increasing dramatically as the comet approached the Sunday. Cyanide can also produce a greenish color under the right conditions. and if the concentrations are high enough, it might explain the vivid hue captured during the eclipse. But there's a third possibility, one that's far more speculative, but worth mentioning because it ties into the broader pattern of anomalies. What if the green glow represents some kind of activation? What if Atlas, whatever it is, crossed a threshold of solar heating that triggered a change in its behavior? Loeb doesn't quite say this directly in his interview, but the implication is there. In his more recent writings, he talks about how the color change happened suddenly, how it appeared to be a threshold effect, rather than a gradual transition. One moment, no green. The next moment, vivid green, like flipping a switch. If Atlas were a technological object in hibernation, traveling through the cold of interstellar space for millions of years, it would need some way to wake up when it reached a new star system. Temperature would be an obvious trigger. As it gets closer to the sun and surface temperatures rise, systems could power on, instruments could activate, and that activation might produce byproducts, heat or light, or chemical emissions that we'd interpret as cometary outgassing. Again, this is speculation. There's no hard evidence for it, but it fits the pattern Loeb keeps highlighting. Atlas behaves almost like a comet, but not quite. It has most of the features you'd expect, but with odd variations. A tail that develops late, a forward glow that shouldn't be there, a color change that doesn't match the spectroscopy. Each individual anomaly has a possible natural explanation, but taken together, they paint a picture of something that's trying very hard to look like a comet without quite succeeding. And then there's the chemical composition. The Webb Space Telescope observed Atlas on August 6th and analyzed the gas in its coma using spectroscopy. What they found was unusual. The ratio of carbon dioxide to water ice is 8:1. 8:1. That's among the highest ratios ever recorded for any comet, natural or otherwise. Most comets in our solar system have much more water ice than carbon dioxide ice. Water is common. It's everywhere. Every icy body we've ever studied, from comets to the moons of Jupiter to the rings of Saturn, is mostly water ice with traces of other compounds mixed in. But Atlas is the opposite. It's dominated by carbon dioxide with only a small amount of water. Why would that be? One explanation is that Atlas formed in a very cold part of its home star system, far from its sun, where carbon dioxide ice is stable, but water ice sublimates away over billions of years. It could be genuinely ancient, older than our solar system, coming from a star that formed when the galaxy was younger and had different chemical abundances. Another explanation is that the carbon dioxide is a recent addition, frost that formed on the surface during Atlas's journey through interstellar space. Interstellar gas clouds contain carbon dioxide. If Atlas passed through one, molecules could condense on its cold surface, building up a layer of CO2 ice over time. Or, and this is where Loeb's argument goes, the CO2 could be a protective layer, a deliberate coating, something designed to insulate the object and regulate its temperature as it travels between stars. Carbon dioxide ice has different thermal properties than water ice. It sublimates at different temperatures, reflects light differently, shields against radiation in specific ways. If you're engineering a probe to survive interstellar space, you might choose CO2 as part of the thermal management system. This is highly speculative, but it's not physically unreasonable. We know carbon dioxide ice behaves differently from water ice. We know it can form stable deposits in the right conditions, and we know that any object traveling through space for millions of years would need some way to protect itself from radiation, micrometeoroids, and temperature extremes. The point Loeb keeps making is that we shouldn't assume. We shouldn't look at the surface composition and conclude that tells us everything about what's underneath. The 8:1 ratio is weird. It's worth noting. It's worth investigating. But it doesn't prove Atlas is natural any more than it proves it's technological. It's just another data point in a growing list of things that don't quite fit the standard model. Chapter 5. Is it alien technology? So, let's address the question directly. The one that Loeb poses in his paper and explores throughout the interview. Is 3E Atlas alien technology? Not could it be, not might it be, but what would we need to see to actually conclude that it is? This is where Loeb's approach becomes interesting, because he's not just throwing out wild speculation. He's trying to establish a framework, a methodology, a way of thinking about interstellar objects that doesn't automatically default to natural explanations, but also doesn't jump to alien conclusions without evidence. In the interview, Loeb talks about something he calls the Loeb scale. It's a rating system from 0 to 10 that he's proposed for classifying interstellar objects based on how likely they are to be technological rather than natural. 0 would be an object that definitely shows all the characteristics of a normal comet or asteroid. It has a tail. It outgasses predictably. Its trajectory matches what you'd expect from gravity and rocket effects. Its composition is typical. Nothing unusual, nothing to see here. 10 would be an object that's definitely technological. It maneuvers in ways that can't be explained by natural forces. It transmits signals. It has artificial structures visible in high-resolution images. It releases heat that doesn't match solar illumination, suggesting an internal power source. It does something that screams intelligence, that leaves no room for doubt. Everything in between is a gradient. An object that shows 1 or 2 anomalies might rate a 3 or 4. Something with multiple unexplained features, statistical improbabilities stacking up, might rate a 6 or 7. The idea is that as we discover more interstellar visitors in the coming years, and we will, the Vera Rubin Observatory is expected to find one every few months, once it's fully operational. We need a consistent way to evaluate them, a triage system, so we know which ones deserve intense scrutiny, and which ones are clearly just space rocks passing through. Loeb suggests that any object rating above 5 on this scale should trigger an international response. Not panic, not military mobilization, but a coordinated scientific effort. We should be using every available telescope, every spacecraft, every observational tool to study it. We should be pooling data internationally because, as Loeb points out, aliens don't care about our borders. They don't care which nation discovered the object or which government has jurisdiction. An interstellar visitor is a problem for humanity as a whole, and the response should be global. He goes further. He says there should be an organization, an international body specifically tasked with monitoring interstellar objects and deciding how to respond if one of them shows technological signatures. Right now, we don't have that. We have NASA, we have ESR, we have various national space agencies that track near-Earth objects and watch for asteroid impacts, but there's no unified protocol for what to do if we detect an interstellar probe. And Loeb argues we need one because the window of opportunity is short. Interstellar objects move fast. By the time we spot them, they're often already deep in the solar system, and we only have weeks or months to study them before they leave. If we waste that time debating who's in charge or whether it's worth investigating, we miss the chance entirely. He draws a comparison to other existential risks. We worry about artificial intelligence. There are conferences, research institutes, government task forces dedicated to making sure AI development doesn't accidentally create something that harms humanity. We worry about climate change. There are international agreements, treaties, summits where nations coordinate their responses. We even worry about asteroid impacts. NASA has a planetary defense program specifically designed to track potentially hazardous objects and develop ways to deflect them. But alien technology, nothing. No organization, no protocol, no plan. And Loeb finds that baffling. He says even if the probability is low, even if there's only a 1% chance that an interstellar object could be technological, the consequences are so significant that we should be prepared. Because unlike a radio signal from a star thousands of light years away, which gives us plenty of time to think and debate and plan, a visitor in our backyard requires immediate action. So, where does Atlas fall on the Loeb scale? He doesn't give an exact number in the interview, but reading between the lines, it's probably somewhere around a 5 or 6. Not definitely technological, but anomalous enough to warrant serious attention. The trajectory is unusual. The mass is higher than expected. The visual appearance has quirks. The chemistry is odd. Each individual feature might have a natural explanation, but collectively they push Atlas into the range where you can't just dismiss it as obviously a comet. And that's really the heart of Loeb's argument. He's not saying Atlas is definitely an alien spacecraft. He's saying it's weird enough that we should be watching it very carefully, and we should be open to the possibility that it might not be natural, because the alternative, dismissing it prematurely and missing a genuine technological visitor, would be a tragedy of historic proportions. Now, Loeb also floats the idea, and this is where things get into darker territory, that if Atlas is technological, it might not be friendly. He references something called the dark forest hypothesis, a concept from science fiction that suggests the universe is full of intelligent civilizations, but they all stay silent because revealing your presence is dangerous. If you don't know the intentions of another species, if you can't be sure they're not hostile, the safest strategy is to stay hidden, to be the predator, not the prey. In this framework, an interstellar probe entering another star system could be a reconnaissance mission, a scout gathering information before a larger force arrives, or it could be the vanguard of an attack, something designed to disable defenses or deploy weapons before the target even knows what's happening. Loeb is careful to frame this as a thought experiment, not a prediction. He says in the interview that Atlas could come to save us or to destroy us, and we should be prepared for both possibilities. But the underlying point is serious. If we detect something technological, we can't just assume it's benign. We need to assess its capabilities, its trajectory, its potential threat level, and we need to do that quickly while it's still far enough away that we have options. What options would we have? Honestly, not many. If Atlas is a spacecraft and it's already in the inner solar system, there's not much we could do to stop it. We don't have weapons that could destroy a 20 kilometers object. We don't have spacecraft that could intercept it. Not at the speed it's traveling. Our best hope would be communication. Try to send a signal. Try to establish contact. Hope that whoever built it is willing to talk. Loeb suggests that if Atlas turns out to be technological, one of the first things we should do is transmit a message. Something simple. Hello. Welcome to our neighborhood. We come in peace. Standard first contact protocol. And then wait. See if there's a response. See if the object changes its behavior in any way that suggests it received and understood the message. But all of that assumes we'd even recognize technological signatures if we saw them. And that's a real problem. We're looking for things that match our expectations of what technology should look like. Radio signals, heat signatures, geometric structures, but an advanced civilization, one capable of building interstellar probes, might use technology so far beyond ours that we wouldn't recognize it as artificial. Arthur C. Clarke famously said that any sufficiently advanced technology is indistinguishable from magic. and that cuts both ways. If Atlas is the product of a civilization 1,000,000 years more advanced than us, it might look completely natural to our instruments. It might use propulsion systems that don't produce exhaust. It might communicate in ways we can't detect. It might be made of materials that mimic natural rock and ice so perfectly that we'd never suspect it wasn't formed by accidental geological processes. This is the challenge Loeb is grappling with. How do you prove something is technological when you don't know what technologies are possible? How do you distinguish design from coincidence? When you're working with a sample size of 1, his answer is that you look for patterns. You look for things that are improbable, but functional. A trajectory that happens to pass near multiple planets could be random, but it's also exactly what you'd design if you wanted to survey those planets. A mass that's high enough to resist perturbations, but low enough to suggest a hollow structure, could be natural. But it's also what you'd expect from an engineered shell. A surface coating of carbon dioxide ice could form naturally, but it's also a sensible choice for thermal protection. None of these things prove anything on their own, but they're suggestive. They're enough to justify asking the question. And Loeb's frustration, the thing that comes through clearly in the interview, is that much of the scientific community doesn't even want to ask the question. They want to assume Atlas is natural, file it away as an interesting but ultimately ordinary comet, and move on. He talks about this resistance, this gatekeeping, as he calls it. He says that mainstream science is often hostile to ideas that challenge established narratives. And the narrative right now is that interstellar objects are natural debris, rocks and ice balls ejected from other star systems during planet formation. Any suggestion that they might be something else, that they might be technological, gets dismissed as pseudoscience or attention-seeking. Loeb's response is that science should follow the data, not assumptions. If the data points towards something unusual, we should investigate. We should be curious. We should be willing to consider hypotheses that make us uncomfortable, because the alternative is intellectual stagnation, closing our minds to possibilities just because they seem unlikely. And he points out that history is full of examples where the unlikely turned out to be true. Continental drift was dismissed as absurd until the evidence became overwhelming. The idea that the sun, not the Earth, is the center of the solar system was heretical until telescopes proved it. Black holes were thought to be mathematical curiosities, with no physical reality until we started detecting them. The pattern is always the same. Someone proposes an idea that contradicts conventional wisdom. The establishment rejects it. Data accumulates. Eventually, the new idea becomes accepted, and everyone wonders why it took so long to see what was obvious in hindsight. Loeb is betting that alien visitors, technological objects from other star systems will follow the same trajectory. Right now, the idea is fringe. Most scientists think it's unlikely or impossible. But as we find more interstellar objects, as we study them more carefully, as the anomalies pile up, eventually, the evidence will become undeniable. And when that happens, Loeb wants to be on record as one of the people who took it seriously from the beginning. Chapter 6. The mass budget doesn't add up. Let's return to the numbers, because this is where Loeb's argument becomes most concrete. The 33 billion ton calculation isn't just a curiosity. It's a constraint. It tells us something fundamental about what Atlas is made of, how it's structured, and whether its existence makes sense given what we know about interstellar space. When Loeb talks about the mass budget in his interview, he's referring to a relatively simple calculation. How much rocky material exists in interstellar space? And given that amount, how often should we expect to see objects of different sizes passing through our solar system? The galaxy contains a certain amount of heavy elements: carbon, silicon, iron, oxygen, all the stuff that makes up rocks and planets and asteroids. Most of this material is locked up in stars and planets. Some of it drifts in interstellar space as dust and small particles, and occasionally, some of it gets ejected from star systems during planet formation, thrown out by gravitational interactions with giant planets, and becomes interstellar debris. When you add up all the ejected material and distribute it across the volume of the galaxy, you get a density. So many tons of rock per cubic light year. It's a small number. Space is big and mostly empty, but we can estimate it based on planet formation models and observations of young star systems. Once you have that density, you can calculate how often an object of a given size should cross paths with our solar system. Small objects are common, so we should see them frequently. Big objects are rare, so we should see them almost never. The distribution follows a power law, and you can work out the expected rate for any size you're interested in. For Atlas, assuming the initial 20 kilometers estimate, Loeb calculated that we should only see an object that large about once every 10,000 years. And even with a revised estimate of 5 to 6 kilometers based on the 33 billion ton mass, the rate is still very low. Maybe once per 1,000 years, maybe once every few thousand years, depending on exactly how you model the interstellar population. But we've only been looking for a decade and we found it. That's the statistical tension Loeb keeps highlighting. It's like predicting that a certain rare bird will fly past your window once every 1,000 years and then seeing it on your first day of birdwatching. Could we just be lucky? Absolutely. Rare events happen. Someone wins the lottery. Lightning strikes. But when you combine this statistical oddity with all the other auditors we've already discussed, the trajectory, the timing, the visual anomalies, it starts to feel less like luck and more like something else. Now, there's another way to resolve this tension. Maybe our estimates of the interstellar mass budget are wrong. Maybe there's way more rocky material floating around out there than we think. If the density of interstellar debris is 10 times higher or 100 times higher, then finding Atlas early in our survey wouldn't be surprising at all. But that creates its own problems. If interstellar space is full of large objects, why haven't we seen more of them? The Vera Rubin Observatory just came online in 2025, and it's finding asteroids at an incredible rate, thousands per week, in our solar system alone. If interstellar objects were common, Rubin should be spotting them constantly. But so far, it's only found a handful of candidates, and most of those are still being confirmed. So, either the mass budget is correct, and Atlas is a statistical fluke, or the mass budget is wrong, and we're about to discover that interstellar objects are far more common than we realized. Either way, something doesn't quite fit. Loeb prefers a third option. Atlas is anomalously massive because it's not a solid rock. It's a structure, a shell, something with a lot of volume, but not a lot of mass per unit volume. That would explain why it weighs 33 billion tons. Enough to resist the thrust from outgassing, but not as much as a solid object of the same size would weigh. Think about spacecraft we build. The International Space Station is huge, but it doesn't weigh much relative to its size. It's mostly empty space with thin walls. If you saw it from a distance and assumed it was a solid chunk of metal, you'd wildly overestimate its mass. The same principle could apply to Atlas. If it's hollow, if it's designed to be lightweight and efficient, it could easily have the mass we're measuring without being impossibly rare. But there's a problem with this hypothesis. We have no direct evidence that Atlas is hollow. We can't see inside it. We can't measure its internal structure. All we have is the trajectory data and the mass estimate derived from the lack of non-gravitational acceleration. And those constraints are consistent with a solid object, just a surprisingly massive one. What we need is a way to probe the interior. Radar would work if we could get close enough. Radar can penetrate surfaces and reveal internal structures. That's how we mapped the interior of comets in our solar system, by bouncing radio waves off them and measuring the echoes. But Atlas is too far away for radar from Earth, and we don't have any spacecraft nearby that could do it. The high-risk camera on the Mars Reconnaissance Orbiter, which will image Atlas on October 3rd, can't see inside objects. It can only photograph the surface, but it might reveal something useful. If Atlas has an unusual shape, if it's too smooth or too geometric, if it shows features that don't match a natural comet, that would be significant. Not proof of anything, but another data point. Loeb is particularly interested in what the high-rise images will show because of how they'll separate the nucleus from the coma. One of the challenges with observing comets is that the bright cloud of gas and dust surrounding them makes it hard to see the solid core. It's like trying to photograph a light bulb while someone's shining a flashlight in your eyes. The glare overwhelms the details. But high-rise has incredible resolution. It was designed to see boulders on the Martian surface, objects a meter or two across from orbit. When pointed at Atlas from a distance of 29 million km, it should be able to resolve features down to about 30 kilometers. That's not enough to see surface details, but it's enough to distinguish the central nucleus from the surrounding coma and get a better size estimate. If the nucleus turns out to be larger than 5 kilometers, if HiRISIS confirms that Atlas really is pushing 10 or 15 or 20 kilometers across, then the mass budget problem gets worse, because a solid object that size, weighing only 33 billion tons, would have to be made of something very light. Porous ice maybe, or a foam-like structure, something that doesn't match typical comet composition. And if that's the case, if Atlas turns out to be anomalously large and anomalously light at the same time, the technological hypothesis starts to look more plausible. Not proven, but plausible. There's another piece of the mass budget argument that Loeb touches on briefly, but is worth exploring. The rate of interstellar objects should depend on how many planetary systems are out there forming planets and ejecting debris. If planet formation is common, if most stars have planets, then the rate should be relatively high. If planet formation is rare, the rate should be low. We now know that planets are common. The Kepler mission and other exoplanet surveys have shown that most stars have planets, so the mass budget calculations assume a high production rate of interstellar debris. Billions of planetary systems churning out rocks and comets and ejecting them into interstellar space over billions of years. That should create a substantial population of wandering objects. But if most of that debris is small, pebbles and boulders, and maybe football field-sized objects, then the big stuff is still rare, and Atlas is still an outlier. Unless, as Loeb suggests, some fraction of interstellar objects aren't natural at all. If even 1% of them are technological probes built by civilizations exploring the galaxy, then the statistics change completely. You don't need a large mass budget of naturally ejected rocks to explain a technological visitor. You just need one civilization, somewhere in the Milky Way, that decided to send probes to nearby star systems. And given how many stars are out there, given how old the galaxy is, that doesn't seem impossible. This is where Loeb's argument connects to the broader question of extraterrestrial intelligence. If we're alone in the galaxy, if Earth is the only planet that ever developed technological civilization, then every interstellar object we detect will be natural rocks and ice. Nothing more. But if we're not alone, if intelligence is common or even moderately rare but still present, then some interstellar objects will be artificial, probes, derelicts, ancient spacecraft drifting through the void. And the question becomes how to tell the difference. How to recognize the artificial ones among the natural background? Loeb's answer is that we need to be systematic. We need to observe every interstellar object carefully. We need to measure their properties, track their trajectories, look for anomalies, and when something doesn't quite fit, when the mass or the path or the chemistry is off, we need to investigate thoroughly, because missing a genuine technological visitor would be one of the biggest mistakes humanity could make. An atlas with its 33 billion ton mass and all its other quirks is exactly the kind of object that deserves that thorough investigation. It's not obviously natural. It's not obviously technological. Is somewhere in between, in the gray zone, where we can't be certain either way. And that uncertainty, Loeb argues, is reason enough to watch it very closely. Chapter 7. Pine, the Sunday, October 29th. That's the date everything hinges on. That's when Atlas reaches perihelion, its closest point to the sun, and disappears from view behind our star. And according to Loeb, that's not just an inconvenient observational gap. It's potentially the most important moment in the entire encounter. When an object reaches perihelion, it's at the point in its orbit where the sun's gravity is strongest. Velocity is highest. The curvature of the trajectory is sharpest. And if you want to make a major change to your orbit, if you want to slow down, or speed up, or alter your course, that's when you do it. That's when a little bit of thrust gives you the biggest change in trajectory. It's called the Orth effect, and it's a fundamental principle of orbital mechanics that every spacecraft designer knows. Normally, we use the Orth effect to speed up. You fire your engines when you're moving fastest, when you're closest to a massive body like the sun or a planet, because that's when the kinetic energy you add has the most impact. Pioneer, Voyager, every probe we've ever sent to the outer solar system use gravitational assists and carefully timed engine burns at perihelion to gain speed and reach their destinations. But the effect works in reverse, too. You can use it to slow down, to brake, to bleed off velocity, and let gravity capture you into a bound orbit instead of an escape trajectory. This is called a reverse Orth maneuver, and it's exactly what you do if you wanted to transition from passing through a star system to staying in it permanently. Atlas is currently on a hyperbolic trajectory. That means it's moving faster than escape velocity. It's going to swing around the sun and head back out into interstellar space. Unless something changes, unless it slows down at perihelion. And the timing is remarkable. On October 29th, when Atlas reaches perihelion, Earth will be on the exact opposite side of the Sunday. We'll be in what's called solar conjunction. The sun will be directly between us and Atlas, and its glare will drown out any observation. Ground-based telescopes won't be able to see anything. Even space telescopes like Hubble and Webb, which aren't affected by daylight, will struggle because the sun's corona and brightness make it nearly impossible to image anything that close to the solar disk. Loeb describes this as a hidden vantage point. If you were designing a trajectory that allowed you to make a course correction unobserved, this would be it. You'd arrive at perihelion when the planet with the most advanced telescopes and the most interest in tracking you is on the far side of the star. And you'd make your maneuver while no one is watching. Is that intentional? Is it deliberate? Or is it just another coincidence in a long string of coincidences? If you take Atlas's trajectory and vary its speed slightly, shift when it arrives at perihelion by a few days or weeks, the probability that Earth would be on the opposite side of the sun at that exact moment is low. Not impossible, but low. Maybe 1 in 20 depending on how you calculate it. Just another improbable thing stacked on top of all the other improbable things. But here's what makes this particularly significant. If Atlas does make a maneuver on October 29th, If it fires engines or uses some propulsion system to slow down and capture itself into orbit around the Sun, we won't know immediately. We'll only find out weeks later when it re-emerges from behind the Sun in late November or early December and we recalculate its trajectory. At that point, if the orbit has changed, if Atlas is no longer on an escape path, but instead on an elliptical orbit that keeps it in the solar system, we'll know something happened. We'll know a maneuver occurred. But we won't know exactly when, or how, or what kind of propulsion was used. All we'll have is the before and after, the trajectory going in and the trajectory coming out. Loeb calculates that if Atlas does capture itself, if it transitions to a bound orbit, it could then make its way to Earth relatively quickly. The timeline, he suggests, is late November to early December for closest approach to our planet. Not close in the sense of a collision. Atlas will still be millions of kilometers away, but close enough that we'd have a much better view of it than we do now. And that raises the question of intent. If Atlas is technological, if it's a probe or spacecraft of some kind, what would it want? What would be the purpose of staying in the solar system instead of just passing through? One possibility is observation. A probe designed to study inhabited worlds would want to stick around. It would want to orbit at a distance where it could monitor radio transmissions, watch for industrial signatures, track the movement of spacecraft and satellites. It would want to gather data over months or years, building a complete picture of the civilization it found. Another possibility is resource gathering. The solar system is full of useful materials: water ice on comets and moons, metal-rich asteroids, helium 3 inches the atmospheres of gas giants. An advanced civilization might send probes to catalog resources and star systems and identify targets for future exploitation. Or the purpose could be defensive. A probe that detects technological signatures, evidence of intelligent life, might be programmed to eliminate it before it becomes a threat. This is the dark forest scenario that Loeb references. The idea that revealing your existence to other civilizations is dangerous because you can't know their intentions. So, the safest strategy is to destroy any emerging intelligence you encounter before it develops the capability to threaten you. Loeb is careful to say he's not predicting this. He's not claiming Atlas is a weapon or that we're in imminent danger, but he is saying that if we detect something technological, we need to assess the full range of possibilities, including hostile ones. We can't just assume benign intent. The good news, if you can call it that, is that we'll have some warning. If Atlas does stay in the solar system, if it captures into orbit and starts maneuvering toward Earth, we'll see it coming. We'll have weeks or months to observe it, to try communicating with it, to figure out what it's doing and what it wants. That's very different from a surprise arrival with no time to react. But the window for that observation is narrow. From late November, when Atlas re-emerges, until late December, when it makes its closest approach to Earth, we have maybe 4 to 6 weeks. And during that time, we need to be watching constantly. We need every telescope, every spacecraft, every sensor we have pointed at it. Loeb mentions in the interview that NASA's Juno probe, currently orbiting Jupiter, might be able to observe Atlas when it passes near Jupiter in March 2026. ESA's JUICE spacecraft will have observations in November. Mars orbiters will track it in early October. We should be coordinating all these assets, pulling the data, making sure we don't miss anything. Because if October 29th is the moment everything changes, if that's when Atlas decides to stay, then we need to be ready for what comes next. And right now, we're not. We don't have a plan. We don't have an organization responsible for handling this scenario. We don't even have a consensus on whether we should be worried. Loeb's frustration with this lack of preparedness comes through clearly in his interview. He keeps emphasizing that we need to take this seriously, even if the probability is low. Even if it's only a 1% chance that Atlas is technological, the potential impact is so significant that we should be treating it as a priority. We should be mobilizing resources. We should be having discussions at the highest levels of government about what to do if an interstellar visitor turns out to be more than just a rock. And yet, most of the response he's gotten from the scientific community has been dismissive. People calling his ideas nonsense. People saying he's chasing attention. People arguing that even raising the possibility of alien technology damages the credibility of serious astronomy. But Loeb's counterargument is simple. Science is supposed to follow the evidence, not assumptions. And the evidence we have for Atlas, while not conclusive, is strange enough to warrant investigation. The trajectory is unusual. The mass is higher than expected. The timing is convenient. The visual appearance has quirks. Each of these things individually might be explainable, but together they create a pattern that deserves attention. And the October 29th moment, the perihelion passed behind the sun, is when we'll start to get answers. If Atlas emerges in late November on the same escape trajectory it went in on, then it's probably just a comet. Unusual one, certainly, but ultimately natural. We can all relax. But if it emerges on a different trajectory, if the orbit has changed, if it's no longer leaving, then we'll know something extraordinary happened. And at that point, the question of whether Atlas is natural or technological will become a lot more urgent. Chapter 8. Prepare for both possibilities. Loeb makes a point in the interview that's easy to overlook, but fundamentally important. He says, "It could come to save us or to destroy us. We'd better be prepared for both possibilities and verify that all interstellar objects are just rocks." That statement encapsulates his entire philosophy about how we should approach interstellar visitors, not with blind optimism, not with paranoid fear, but with careful, systematic observation and a willingness to consider the full spectrum of possibilities. The saver scenario is what most people think of when they imagine first contact. An advanced civilization having achieved interstellar travel would presumably have solved the problems that threaten emerging species. Resource scarcity, environmental collapse, self-destructive conflict. They'd be post-scarcity, post-violence, enlightened in ways we can barely imagine. And they might share that knowledge with us. Technology, medicine, solutions to the challenges we face. It's a hopeful vision, Star Trek diplomacy, peaceful exchange of ideas between species. And it's not impossible. If intelligence is common in the universe, if technological civilizations arise frequently, then at least some of them probably develop in benign directions. They overcome their destructive tendencies. They build stable, peaceful societies. And they reach out to younger civilizations with offers of help rather than threats. But the destroyer scenario is equally plausible from a certain perspective. And this is where the dark forest hypothesis enters the picture. Though Loeb is careful not to dwell on it too much in the interview. The basic idea is this. The universe has finite resources. Stars, planets, raw materials, energy. If intelligent life is common, then competition for those resources is inevitable. And if you encounter another civilization, you face a fundamental problem. You don't know their intentions. You don't know if they're peaceful or aggressive. You don't know if they'll compete with you for resources or try to eliminate you preemptively. In that situation, the safest strategy might be to strike first, to destroy any emerging civilization you detect before it becomes powerful enough to threaten you. Not out of malice, but out of rational self-interest. It's a grim calculus, but it's not irrational. Loeb doesn't endorse this scenario. He's not saying it's what he expects, but he is saying we can't rule it out. If Atlas is a probe, if it's technological, we don't know who built it, or what instructions it's following. It could be a peaceful explorer, or it could be something far more dangerous. And that's why he emphasizes preparation. We need to be ready for both possibilities. We need to have protocols in place for how to communicate if the visitor is friendly, and how to defend ourselves if it's not. The challenge is that we're not prepared for either scenario. We have no agreed-upon method for transmitting messages to an extraterrestrial intelligence. No international consensus on what we should say or who should speak for humanity. And we certainly don't have any way to defend against an advanced technological threat if one materializes. Our most powerful weapons, nuclear missiles, wouldn't do much against an object the size of Atlas, even if we could intercept it, which we can't at the speed it's traveling. Destroying a 20 kilometers object would just create thousands of smaller fragments still on collision course. We'd make the problem worse, not better. And if Atlas has propulsion, if it can maneuver, then targeting it becomes even more difficult. A moving target that can dodge is nearly impossible to hit with the kinds of weapons we have. We'd need technology we don't possess. Directed energy weapons, maybe high-powered lasers or particle beams. Systems that can deliver energy at the speed of light. So there's no time for evasion. But we don't have those. Not at the scale needed to affect a massive object. Not with the power output required. We're decades away from that kind of capability at minimum, maybe centuries. So, if Atlas turns out to be hostile, our options are extremely limited. We could try to communicate, try to negotiate, try to convince whoever or whatever controls it that we're not a threat. But if that fails, we're out of moves. This is why Loeb argues so strongly for establishing an international organization to handle these scenarios, because the decisions that need to be made, the actions that might be required, can't be left to individual nations acting independently. They require coordination. They require a unified response from humanity as a whole. He draws parallels to other global challenges. Climate change requires international cooperation because emissions from one country affect the entire planet. Nuclear proliferation requires treaties and monitoring because one rogue state with weapons threatens everyone. Pandemics require coordinated public health responses because diseases don't respect borders. An interstellar visitor, whether peaceful or hostile, is an even more fundamental challenge. It's not a human problem or a national problem. It's a planetary problem, and it requires a planetary response. But right now, we don't have the institutional infrastructure for that. The United Nations has committees on space exploration and planetary defense, but they're focused on asteroids and orbital debris, not interstellar visitors. There's no body specifically tasked with monitoring for technological signatures or coordinating responses to potential contact scenarios. Loeb proposes that this needs to change. We need an organization with the authority and resources to track interstellar objects, analyze them for signs of technology, and make recommendations about how to respond. It should be international, with representatives from major spacefaring nations and input from the scientific community. And it should have clear protocols, decision trees. If we detect this signature, we do this. If we observe that behavior, we escalate to this level of response. Without those protocols, we're flying blind. We're making it up as we go. And when you're dealing with something as potentially significant as first contact with an alien intelligence, making it up as you go is a recipe for disaster. Loeb also talks about the need for verification. He says, we need to verify that all interstellar objects are just rocks. Not assume, verify. That means observing them carefully, measuring their properties, looking for anomalies, and when we find something unusual, investigating thoroughly instead of dismissing it. This is where his proposed Loeb scale comes back into play. Every interstellar object gets rated 0 to 10 based on how many unusual features it has, and anything above 5 triggers a coordinated international observation campaign. All available telescopes, all spacecraft in the vicinity, maximum effort to characterize the object and determine its nature. For Atlas, that campaign should already be underway. We should have dozens of telescopes tracking it. We should be coordinating observations from Mars orbiters, from JUICE, from Juno. When it gets close enough, we should be pulling data and analyzing it in real time, looking for any sign that Atlas is behaving in ways that natural objects don't. And yet, from what Loeb describes, that's not really happening. There are observations, certainly individual teams using Hubble and Webb and ground-based telescopes, but there's no unified campaign, no central coordination, no systematic effort to answer the question of what Atlas really is. Part of the problem is that most astronomers are convinced it's just a comet. They see the coma, the tail, the outgassing, and they conclude it's natural, case closed. And once you've reached that conclusion, there's no incentive to keep observing. You move on to the next interesting object. But Loeb argues that conclusion is premature. Yes, Atlas has cometary features, but it also has features that don't quite fit. The trajectory, the mass, the timing, the chemistry. Those anomalies don't disappear just because we found a tail. They're still there. They still need explanation. And until we have good explanations, until we can account for all the auditors in terms of natural processes, we shouldn't close the case. We should keep watching, keep measuring, keep asking questions, because the cost of being wrong, of dismissing a genuine technological visitor as just another comet, is incalculable. We'd miss the opportunity to learn from an advanced civilization. We'd miss the chance to establish contact. We'd miss the warning signs if the visitor turned out to be hostile. Loeb's frustration is palpable when he talks about this. He feels like he's shouting into the void, warning about a possibility that no one wants to take seriously. And he knows that if he's right, if Atlas does turn out to be something more than a rock, people will look back and wonder why we didn't investigate more carefully when we had the chance. Chapter 9. The Scientific Backlash. Now, we need to talk about the other side of this story. Because Loeb's claims haven't been made in a vacuum, they've provoked a strong response from the astronomical community. And much of that response has been critical, sometimes harshly so. NASA's Tom Statler, who serves as the AWI's program scientist for small bodies, has been one of the most vocal critics. He stated repeatedly that all available data points to Atlas being a natural comet. The brightness variations, the outgassing, the development of a tail. All of it matches what we'd expect from an icy body heating up as it approaches the Sunday. There's nothing in the observations that requires invoking alien technology. Statler points out that comets are inherently unpredictable. Even ones from our own solar system behave in ways that can seem anomalous until you understand the physics. They brighten and dim irregularly, as different patches of ice sublime. They develop jets that push them in unexpected directions. They fragment and reform. They're messy, complex objects, and Atlas fits that pattern perfectly. The early brightness, the thing that led to the initial 20 kilometers size estimate, can be explained by a large coma forming far from the Sunday. If Atlas is particularly rich in volatile compounds, substances that sublime at low temperatures, it could start outgassing earlier than typical comets. That would create a bright cloud of gas and dust that makes the object look bigger than it really is. The trajectory alignment with the ecliptic plane, the 1 in 500 coincidence, isn't as unusual as it might seem when you consider observational bias. We're more likely to detect objects that pass through the inner solar system near the plane where the planets orbit, because that's where most of our telescopes are pointed. Objects coming in at steep angles perpendicular to the ecliptic might pass through the solar system without being detected at all. The close approaches to multiple planets could also be selection bias. We notice interstellar objects that pass near planets because those encounters are interesting. We write papers about them. We point at them. Objects that don't pass near anything notable might go unobserved or unremarked. Chris Lintott from Oxford University has been even more blunt in his criticism. He called Loeb's alien technology hypothesis absolute nonsense. He argues that proposing exotic explanations for phenomena that have straightforward natural interpretations is bad science. It's the modern equivalent of seeing lights in the sky and immediately concluding they're flying saucers instead of considering mundane explanations like aircraft or satellites or atmospheric phenomena. Lint and others have pointed out that this isn't the first time Loeb has made claims about interstellar objects being alien technology. He did the same thing with Oumuamua back in 2017, arguing that its unusual acceleration could be explained by a light sail, a thin reflective sheet pushed by solar radiation. That claim was widely criticized by other astronomers, who showed that natural outgassing could explain the acceleration just as well. The pattern critics say is that Loeb takes any interstellar object with slightly unusual properties and immediately jumps to the alien hypothesis. It's sensationalism, it's attention-seeking, and it damages the credibility of legitimate research into extraterrestrial intelligence. Scientists from SETI, the Search for Extraterrestrial Intelligence, have been particularly frustrated. Organizations like the SETI Institute are dedicated to finding evidence of alien civilizations using radio telescopes to listen for signals from other star systems. They take the search seriously. They follow rigorous protocols. They're careful not to make claims without solid evidence. And then Loeb comes along and declares that every weird space rock might be an alien probe, and suddenly the entire field looks less credible. People who are already skeptical of SETI, who think searching for aliens is a waste of resources, point to Loeb's claims as evidence that the whole enterprise is pseudoscience. The frustration from the SETI community is that they're trying to do careful, methodical science, and Loeb's high-profile speculations make their work harder. It becomes easier for critics to dismiss them, easier for funding agencies to cut their budgets, easier for the public to lump legitimate research in with conspiracy theories about UFOs and ancient astronauts. But Loeb's response to these criticisms is consistent. He argues that science should be driven by data, not by concerns about credibility or reputation. If the data suggests something unusual, we should investigate, even if the hypothesis makes us uncomfortable, even if it challenges our assumptions about what's likely or possible. He points out that the history of science is full of examples where the consensus was wrong. Continental drift was dismissed as impossible for decades before the evidence became overwhelming. The idea that bacteria could cause ulcers was ridiculed until it was proven correct. Black holes were thought to be mathematical curiosities with no physical reality until we started detecting them. In every case, the people proposing the unconventional ideas were criticized, mocked, told they were damaging their fields, and in every case, they turned out to be right. Not because they were smarter than their critics, but because they followed the data instead of the consensus. Loeb sees himself in that tradition. He's not claiming certainty. He's not saying Atlas is definitely alien technology. He's saying it's anomalous enough that we should investigate carefully, and we shouldn't dismiss the possibility just because it seems unlikely. And he makes a pragmatic argument. Even if the probability that Atlas is technological is only 1%, the implications are so significant that it's worth taking seriously, because if we're wrong, if we dismiss it as a comet and miss a genuine encounter with alien intelligence, that's a mistake we can never undo. The object will leave. The opportunity will be gone, and we'll spend the rest of human history wondering what we missed. On the other hand, If we investigate thoroughly and conclude it's natural, we've lost nothing, except some telescope time and research effort. The cost of a false positive, of investigating a natural object as if it might be technological, is minimal. The cost of a false negative, of missing a technological object because we assumed it was natural, is enormous. This asymmetry, Loeb argues, should shift our approach. We should err on the side of investigation. We should look carefully at every interstellar visitor, especially the unusual ones, and only conclude they're natural after we've ruled out alternatives. But the mainstream scientific community doesn't see it that way. They see resources as limited, telescope time as precious, and they don't want to waste either on wild goose chases. If an object looks like a comet, acts like a comet, and has a straightforward, natural explanation for its properties, then it's a comet. Moving on. The debate really comes down to different philosophies about how science should work. Should we be conservative, sticking with established explanations until they're proven wrong? Or should we be exploratory, considering unconventional possibilities even when conventional ones are available? Loeb is firmly in the exploratory camp. He'd rather investigate 100 natural objects, as if they might be technological, and find nothing than miss one genuine technological object, because he dismissed it too quickly. His critics are more conservative. They want strong evidence before entertaining extraordinary hypotheses. And, to be fair to the critics, they have a point. The claim that an interstellar object is alien technology is extraordinary. It would overturn our understanding of how common intelligence is in the universe. It would confirm that we're not alone. It would raise profound questions about the intentions and capabilities of whoever built the object. Extraordinary claims require extraordinary evidence. And so far, the evidence for Atlas being technological isn't extraordinary. It's suggestive at best. The trajectory is unusual, but not impossible. The mass is high, but not inconsistent with a dense comet. The visual features are quirky, but explainable. The chemistry is odd, but within the range of natural variation. Nothing about Atlas definitively screams artificial. So the critics argue we should go with the simpler explanation. It's a comet from another star system. Interesting one, certainly worth studying, but ultimately just a natural object following natural laws. No aliens required. Where this leaves us is in a state of uncertainty. The data we have isn't conclusive either way. Atlas could be natural. It could be technological. We don't have enough information to say for sure. And that uncertainty is precisely why Loeb keeps pushing for more observations, more measurements, more careful study. Because the only way to resolve the question is to gather better data. Chapter 10. What happens next? So, here we are. October is just beginning. Atlas is still visible in the night sky, though fading as it gets closer to the sun and the solar glare intensifies. And over the next 4 weeks, we're going to get answers to some of the questions that have been building throughout this entire story. October 3rd is the first major milestone. That's when Atlas makes its closest approach to Mars, passing within 29 million kilometers of the red planet. NASA's Mars Reconnaissance Orbiter will be ready, its high-rise camera pointed toward the interstellar visitor. The resolution should be good enough to separate the nucleus from the surrounding coma, giving us the clearest view yet of what Atlas actually looks like at its core. If HIRIS reveals a nucleus that's larger than 5 kilometers, if it confirms that Atlas is pushing toward the 10 or 15 kilometers range, that strengthens Loeb's argument about the mass budget problem. A large, relatively lightweight object that resists perturbations from outgassing starts to look less like a natural comet and more like something with an engineered structure. If the nucleus is small, just a few km or less, then the 33 billion T-mass estimate might need revision. Maybe the method used to calculate it has systematic errors. Maybe the outgassing is more asymmetric than assumed, creating thrust that cancels out in ways we're not accounting for. A small nucleus would push Atlas back toward the natural comet explanation. ES's Mars Express and ExoMar Trace Gas Orbiter will also observe Atlas during the Mars flyby. They'll use spectrometers to analyze the composition of the coma, looking for molecules that might tell us more about where Atlas formed and what it's made of. More carbon dioxide, more cyanide, something unexpected. Every measurement adds to the picture. And then there's the possibility, remote but real, that Atlas might deploy something during the Mars encounter. A smaller probe, a lander, anything that breaks away from the main body and makes a course correction toward Mars. Loeb calculated that the ejection velocity needed wouldn't be huge, just a few km divided by s. From Earth, we probably wouldn't see it. The object would be too small, too faint, but Mars orbiters might detect it, especially if it's actively maneuvering. Is that likely? No, almost certainly not. But it's the kind of thing we should be watching for, because if it happens, if something separates from Atlas and heads toward Mars, that would be a game-changer. That would be evidence of technology that no natural process could explain. After the Mars encounter, Atlas continues inward. Through October, it gets closer and closer to the Sun, brightening in the sky, but also getting harder to observe as it approaches the solar glare. Ground-based telescopes will lose sight of it by mid-October. Space telescopes might hold on a bit longer, but even they'll struggle as Atlas gets within a few degrees of the Sun from our perspective. And then, October 29th arrives. Perihelion, the moment of truth. Atlas reaches its closest point to the Sun, about 1.4 astronomical units, just inside the orbit of Mars. And it's on the opposite side of the Sun from Earth, hidden, unobservable. If Atlas is going to make a maneuver, this is when it would happen. This is the optimal moment for a reverse whiff burn. Using the Sun's gravity to amplify the effect of any propulsion system, a relatively small change in velocity at perihelion could be enough to transition from a hyperbolic escape trajectory to an elliptical bound orbit. We won't see it happen. We won't detect the maneuver in real time. We'll only know afterward, when Atlas re-emerges from behind the Sun in late November and we recalculate its orbit. If the trajectory has changed, if it's no longer on an escape path, that will tell us something happened, something significant. November brings a new phase of observations. ESA's JUICE spacecraft, currently en route to Jupiter, but still relatively close to the Sun, will have one of the best views of Atlas as it emerges from solar conjunction. JUICE will observe with multiple instruments, cameras, spectrometers, particle detectors. The data won't arrive immediately because JUICE is far from Earth and using a low bandwidth antenna, but eventually, probably by February 2026, we'll get detailed measurements from this period. If Atlas is particularly active after perihelion, if it's outgassing heavily or showing unusual brightness variations, JUICE might catch it. And if there are any signs of artificial activity, any anomalies that can't be explained by natural cometary processes, that's where we'd see them. Late November and early December is when Atlas makes its closest approach to Earth. Not close in the sense of a near miss. We're talking about 1.8 astronomical units, roughly 170 million miles, but close enough that our best telescopes will have excellent views. Hubble, Webb, ground-based observatories with adaptive optics. All of them will be pointed to Atlas, capturing data at multiple wavelengths. This is the window where we'll have the best chance to characterize the object fully, to measure its rotation rate, its shape, its composition, and detail, to look for anything unusual, anything that doesn't fit the comet model. And then Atlas moves on. It continues past Earth, heading out toward the orbit of Jupiter. In March 2026, NASA's Juno spacecraft will observe it as it passes near Jupiter. That's another opportunity for close-range measurements, another chance to catch something we might have missed earlier. After that, Atlas either leaves the solar system, continuing on its hyperbolic trajectory out into interstellar space, or it stays, orbiting the Sun on whatever path it established at perihelion. If it leaves, we'll watch it fade into the distance, eventually becoming too dim to track. And we'll add it to the list of interstellar visitors, a fascinating object that raised interesting questions, but ultimately turned out to be natural. If it stays, everything changes. An interstellar object that captures itself into our solar system, deliberately or otherwise, becomes a permanent fixture, something we can study for years or decades, something we can potentially send spacecraft to visit, and something that might respond if we try to communicate. Loeb's point throughout this entire interview, throughout all his writings about Atlas, is that we need to be ready for either outcome. We need to watch carefully. We need to gather good data. We need to be prepared to respond if the object turns out to be more than just a rock. Because this is only the beginning. The Vera Rubin Observatory is now operational, scanning the sky with unprecedented efficiency. It's finding new asteroids by the thousands. And among those discoveries, we're going to find more interstellar objects. Maybe one every few months. Maybe more often than that if they're common. Each one will be an opportunity. A chance to study material from another star system. A chance to learn about planet formation in other parts of the galaxy. And maybe, just maybe, a chance to encounter something that wasn't formed by natural processes at all. Loeb wants us to be systematic about this, to rate each interstellar object on his scale, to investigate the unusual ones thoroughly, to not dismiss possibilities just because they seem unlikely, because the universe is full of surprises, and the biggest mistake we could make is to stop looking just because we think we already know what we're going to find. Atlas is a test case. It's the third interstellar visitor we've detected, and it's by far the most controversial. The debate around it, the arguments between Loeb and his critics, are setting the tone for how we'll approach future discoveries. Will we be conservative, sticking with natural explanations unless forced to consider alternatives? Or will we be exploratory, investigating carefully and keeping an open mind? The answer to that question matters because it determines what we'll see. If we assume everything is natural, we'll interpret every observation through that lens, and we'll miss technological signatures, even if they're present. But if we're too eager to see aliens everywhere, we'll waste resources chasing false leads and lose credibility. The balance is difficult. It requires good judgment. It requires following the data rather than our preconceptions. And it requires humility. Admitting that we don't know everything, that the universe might surprise us in ways we haven't imagined. Whatever Atlas turns out to be, whether it's a comet or something more, it's already taught us something valuable. It's shown us that interstellar visitors aren't just theoretical curiosities. They're real objects that we can detect and study, and some of them have properties unusual enough to make us question our assumptions. That questioning, that willingness to look carefully at the anomalies instead of dismissing them, is what science is supposed to be about. Not blind acceptance of radical ideas, but not reflexive rejection either. Just careful observation, good measurements, and honest analysis of what the data tells us. The next few months will be crucial. October 3rd, October 29th, late November, early December. Each of these moments brings new data, new observations, new pieces of the puzzle. And by the time we reach the end of the year, we'll have a much clearer picture of what 3 Atlas really is. Until then, we watch, we wait, and we wonder. This has been an exploration of one of the most intriguing objects ever detected in our solar system. An interstellar visitor that challenges our understanding and pushes the boundaries of what we think is possible. Whether Avi's hypothesis proves correct, or whether Atlas turns out to be an exotic but ultimately natural comet, the questions it raises are profound. We've walked through the trajectory analysis, the statistical improbabilities, the mass calculations, the visual anomalies, the chemical mysteries. We've heard Loeb's arguments and the counter-arguments from his critics. We've explored what it would mean if Atlas were technological and what we should do about it. The story of Atlas is still being written. October 29th is coming, and when that day arrives, when Atlas disappears behind the sun and either stays or leaves, we'll know a little bit more about our place in the universe. Thank you for spending this time exploring this mystery with me. If you found this deep dive valuable, I'd appreciate it if you'd hit that like button and subscribe for more content like this. The universe is full of mysteries, and we're just getting started uncovering them. Before I let you go, I should mention that all the claims discussed here are based on publicly available data and published research. The interpretation of that data, particularly Loeb's hypothesis about potential technological origins, remains controversial within the scientific community. Most astronomers believe Atlas is a natural comet, but the anomalies are real, the questions are valid, and the conversation is worth having. Stay curious, keep looking up, and remember that the universe has surprised us before and will undoubtedly surprise us again. Good night.